welcome back to my channel. Today we'll be learning about the Norton'S theorem, and in my previous video we learned about the Thevenin's theorem and how to find the Thevenin's equivalent circuit. Today we'll be adding the Norton's equivalent circuit with the Thevenin's equivalent circuit. But before that, what do we mean by the Norton's theorem? The Norton's theorem states that any linear circuit with voltage sources or current sources and resistors can be replaced by a current source I subscript SC in parallel with a resistor R. As far as its appearance from the outside is concerned, any two-terminal circuit of resistors and energy sources can be replaced by a parallel combination of an ideal current source and a resistor R, where I is the short circuit current of the network and R is the resistance that will be measured between the output terminals if the energy source were removed and replaced by their internal resistance. And we learned from the Thevenin's theorem that the resistor is connected in series with the voltage of the output of the open circuit. So in Norton's theorem, the resistor is connected parallel to the current source, the ideal current source in the Norton's theorem. And I will show you a diagram so that it will be easy for us to understand. Okay, here is a circuit that contains an arrangement of resistors, voltage sources and current sources. So with a Thevenin's equivalent circuit, we know that the resistors are replaced by an equivalent and ideal resistor, only one resistor, where the voltage sources are replaced, or where the energy sources or the voltage sources are replaced by only one ideal voltage of the open circuit. So back to the Norton's theorem. The Norton's theorem, with this one, the resistor is not connected in series. The resistor is connected in parallel with the energy source. Here in the Norton's theorem, the energy source is the current, the ideal current of a short circuit. So their differences are: this is an open circuit, this is a short circuit. The resistor is connected parallel to the energy source, where the resistor is connected in series with the energy source, where in Norton's theorem the resistor is connected in parallel with the energy source. Also, the energy source in here in the Thevenin's equivalent circuit is the voltage of the open circuit, where here the energy source here is the ideal current in a short circuit. So between these circuits, a formula or a relationship is built, where the resistor R here is equal to the R here. So a relationship is built, and R is equal to the voltage of an open circuit over the current in a short circuit. So this is the relationship that is built between the Thevenin equivalent circuit and the Norton equivalent circuit. So through substitution, you can get your current in a short circuit and your voltage in an open circuit. Okay, let us take an example. So if you look at this circuit is given to us, and it said that we should find the Norton's equivalent circuit and the Thevenin's equivalent circuit of this complex circuit. So first of all, I have to look at the output, where the output is, where the end of the terminals are. So here, since there is nothing connected to this line, you can see that there is no current. The current will not flow through R2. There will be no current flowing through R2. So here and here there will be no voltage drop to from here. So simply we must find the voltage of the open circuit using the voltage source here, using the voltage source, the R1 and the R2, to find the voltage at the open circuit. So at first we must use the divider rule, the voltage potential divider. So we in my later or in my last video we learned about, I taught the voltage potential divider, and it's very simple. So this is how we go about it. So here the V is the voltage source where the R1 and R2 are here. Since we don't consider the R3 because in Thevenin's theorem, the circuit is an open circuit. It's not closed, or it's not the R is not in parallel. So now put our figures in where R1 is 10, R2 is also 10, and our V is 30. So we simplify it, then we get 30 multiplying 1/2, and we're getting 15 volts. So our voltage of the open circuit is 15 volts. Now we have to find the total resistance. Remember, I didn't say this earlier, but the total resistance is equal to the resistance that we need to find so that we can calculate for the current in the short circuit. So we have R equals R of T, giving us this. But first, let's look at this circuit. You can see that this and this are connected in series, where this R3 is connected in parallel, or this and this is connected in series while this is connected in parallel. So you can go in any ways, but now I'm taking R2 and R3. No, I'm adding R2 and R3 in parallel first before adding it to R1 in series. I hope it's understood. A simple addition of resistors. So R2 is parallel to R3, then we do it. This is very simple, and it's adding parallel resistors. So we have our R1 multiplying R3, all divided by R2 plus R3. So we put in our values, we get, remember, all of the resistors are in kilo. That's 10 kilo multiplying 10 kilo, all in one. So let's simplify it so that we won't waste much more time. So we get 100/20 all in kilo. Then our final answer becomes 5 kilo ohms. Remember, we are not done. We have to add what we got to R1 because we added the R2 and R3 in parallel. So we have to add the R1 too. And remember, the R12 is 10 kilo ohms, and here we have 5 kilo ohms. So if we add all of them, we will get 15 kilo ohms. So now we have gotten our voltage in the open circuit and our resistance in this circuit, total resistance in this circuit. So let's move on to find the the ideal current in the short circuit, and also draw our Thevenin's and Norton's equivalent circuit. So here we all know the general formula that I showed you. That's R equal to the voltage in an open circuit over the current in a short circuit. Now we all have the voltage in the open circuit and the current in the short circuit. It's just a matter of substitution. Then we have the voltage in the open circuit over the total resistance. That will be 15k, and if we do the maths, we get 15 over 15 kilos, 15 kilo. That's giving us 1 milliampere. We give us 1 milliampere. Now we have found our current at the short circuit. Okay, so now we have to draw our Thevenin's equivalent circuit. Remember, don't forget, in a Thevenin's equivalent circuit, the resistor is connected in series with the voltage source, or the open circuit, the voltage of an open circuit. So remember that the voltage in an open circuit, we got 15 volts, and the resistor, we got 15 kilo ohms. So this is how we draw your Thevenin's equivalent circuit, and this is how we draw the Norton's equivalent circuits. Also remember, with the Norton's equivalent circuit, the resistor is placed parallel to the current of the short circuit, and in this case we got the current of the short circuit as 1 milliampere. So here's the 1 milliampere, and I hope it's very simple for us to understand. Thank you very much. Have a good day. Bye.